So I'm Greg Heileman, and my colleague presenter is Hayden Free. Hayden, if you want to reach either of us, I've got Hayden's, he's a computer science graduate student at Georgia Tech, so hayden.free at jodtech.edu, and I'm a faculty at the University of Arizona. Feel free to reach out to us if you have any interest in the toolbox that we've created around curricular analytics. And so just a little bit of context, because I think it's a little maybe different than maybe some of the other talks in this session. You know, this is a typical situation in higher education where everyone's blaming everyone else, this circle of blame for why we don't have enough trained engineers coming out of our universities. We tend to blame it on the high schools for not producing students who can successfully pass our classes, and on and on and on. What's happened over time, though, is that in higher education, we're being held to performance-based funding models, various things that really put the pressure on us to graduate and successfully complete students. And from a position of national competitiveness for the United States, producing students in this area and around the world, right? You need to be able to produce high-tech workers, and it's something that is a real challenge. And it's interesting that over the years, people have created models for trying to understand, like, why do students leave universities? And this is kind of one of the more famous models by Vincent Tinto that looked at what causes a student to leave higher education. And I've circled kind of this piece there that's the institution itself, what's happening at the institution. And it says academic performance, faculty, staff interactions. How do you measure that? Like, you could look at the performance, students' grades, you can look at their development, but these are kind of difficult things to measure. So there was kind of a gap in this area, and this is where we've kind of made a contribution. Over the years, there have been a huge number of studies that look at this other thing that I've just circled here, and that's prior student preparation. We measure that, test scores, how students have done in high school, and you can make pretty accurate predictions on how students might do in college. And by the way, this is one of the easiest ways to kind of change this model is simply change your input. There's a handful of institutions around the country that can actually manipulate the input and get better outputs, right? These are the highly selective institutions, but most of the 6,000 or so institutions in this country can't do that. They have to serve who they admit, and they have to figure out how to improve this system. So manipulating the input is not something that most of us have the luxury of being able to do. What we did is then we said, okay, there's many pathways a student could follow through higher education, many pathways even within a given degree, a single degree program. And so we kind of put this term curricular analytics around it. We came up with these two independent factors that we use to quantify the complexity of a curriculum that a student's trying to complete. One is how you teach, how you support a course. And this is where most of the effort was in higher education, people putting tutoring centers, peer mentors, all of these types of things aimed at trying to help the student graduate. But then there's the structural factors. How do you structure your curriculum? And this was the piece that was largely ignored that we've tried to quantify. And so we came up with this theory, of curricular analytics, which is basically a framework for studying how curricula impacts a student's ability to complete a curriculum, how you structure it. And there's a reference there. How it's been used, people have used it to kind of better understand how this impacts student success, the role that curriculum plays in that, compare curricula one institution to another, design new curricula based on others that are out there, redesign a curriculum. Many institutions now around the country require the use of this tool as a part of their academic program review process, which is required by our regional accreditors throughout the United States. If you're going to give federal financial aid, you have to be able to show that you're doing this type of work. And then many students need specialized pathways. They are coming with a background where they've maybe had additional courses in high school that they'd like to apply, and so they need a pathway that's not the typical one that's provided. And then finally, transfer articulation is a place where this is being used. How do students go from community college to four-year institution as efficiently as possible? Probably the most inequitable thing in all of higher education that's happening right now is in transfer articulation. On average, students lose 30 credit hours every time they transfer, and that's a huge loss. And it's also an equity issue, because who goes to community colleges quite a bit different than who goes to universities. So here's how it works. If you use our toolbox, curricular analytics, and then curricular visualization, and I'm going to read a CSV file that's got a degree plan stored in it, and then I'm going to visualize it, and it'll produce this graphic for you, and you can hover over various terms, and it'll give you information about the complexity of this curriculum. So here's a curriculum, and I'm going to show you another one. So think about which one you'd rather be going to school at, or where you'd like to send your kid or brother or sister. So here I'm hovering over Calculus 1, and you'll see that calculus course blocks 10 other courses in this curriculum. You can't take those courses unless you pass Calculus 1, and it's on a path of length 5 through this curriculum. So it turned out that if you correlate both that blocking factor, right, and then we call it the delay factor, the long path through the curriculum, they correlate pretty nicely with a student's ability to complete that curriculum on time. And so then if you look at the most central course in this curriculum, something that we're finding is quite interesting, tends to be the same across the disciplines. Circuits 1, this is a EE program. Circuits 1 is the most central course in almost any EE program that you can look at. Here is an identically accredited program, identical program, EE program, same ABET accreditation, which means it has the identical learning outcomes. It has 4 times the complexity of their program, right? Math courses, Calc 1 is blocking 27 other courses in this curriculum. There's a path of length 10 in this curriculum. Dramatically different. Now, which one would you rather go to? Who'd rather go to the first one? Probably, right? What was interesting is that when we first started doing this work, people would say, well, yes, we're really complex because we're really good. And so we said, well, let's take a look at that. By the way, most central course in this curriculum, Circuits 1, although a lot more prerequisites to get to that course. What we've been able to show, and this is kind of what I've alluded to, is that as complexity score, this is at Utah State University, as complexity increases, the ability to complete a program in 4 years decreases, that's a big deal because you get financial aid for a certain number of years. Students actually end up leaving majors if they think they can't finish on time in many cases. So then this is answering this question about, yeah, I'm complex, but I'm really good. So we said, well, let's look at the rankings of EE programs around the country. All of the programs in the study have identical ABET accreditation, which means they have the same 7 learning outcomes, right? So they're not producing, they're all producing basically the same type of an engineer, right? If you look at the schools that are in the highest tier of quality, we're calling it, this is quality where we're using ranking as a surrogate for quality, and you'll see that the average complexity, and that little notch is a confidence interval, you'll see that the average complexity is under 100. And that first institution I showed you was Cornell University. The second one I'm not going to say, but it's in the third it's in the bottom quartile of rankings. And so what we found is that actually ranking and curricular complexity tend to be correlated, which is quite interesting phenomena. We found the same in computer science. Higher rated computer science programs tend to offer less complex programs. So it's very, very interesting. This tends to make faculty who want to dismiss this, they tend to take note when we show them this. So what we created was a collection of toolboxes, a collection of packages in this toolbox. The first being this CurricularAnalytics.jl. It's kind of aimed at institutional researchers at universities. If they want to do some analysis of their own curricula, they can use this and programmatically, investigate their own curricula. We've got the visualization package, which is just a wrapper around Vue.js. And then we've got an optimization package that does some fairly sophisticated stuff trying to figure out optimized pathways through degree programs, optimizing transfer plans, trying to figure out how, what's the best way to apply credits in order to earn a degree. And then we've got an API that we built that allows you to basically get this running as an engine and then have a web app that's calling this engine and it'll do the computation for you. So as an example of that API, we built a website called CurricularAnalytics.jl that has now thousands and thousands of curricula in it. Many people are doing studies of curricula based on using this tool. And so you can go in there, create an account, and that API is used to call the engine that's computing the metrics that I've just showed to you. And this is an example at New Mexico State University microbiology program within that application, again, using that API. So the last thing I'm going to do is just spend a little bit of time talking about the optimization problems that we have that we're solving in there, because I think they're kind of interesting to this Julia community. So this first one, you're given a curriculum. So what's the difference between a curriculum and a degree plan? So a curriculum is just the collection of courses that if you take those courses, you satisfy the degree requirements and we're going to give you the degree. A degree plan is how you organize that curriculum year over year. And it turns out how you structure that plan can make a difference in whether or not a student can complete that plan. One of the things we find is that in many engineering programs at one institution I was at, every single student in the first semester had calculus and physics and in the same term. We found out that for students with certain math scores, putting calculus and physics together in the very first term was a toxic combination. You're going to improve your grad rates about 10% or retention rate about 10% by just separating them. You don't need to, you can take calculus and put off physics one semester and still have a 4-year plan. They weren't doing it. Then just being able to determine whether or not degree requirements are satisfied. Degree requirements are huge Boolean formula over thousands and thousands of variables over the courses that you offer at an institution. Huge number of ways in which you can satisfy a set of degree requirements. And so the search space is massive in this problem, trying to figure out the best way to satisfy a set of degree requirements. We're using it for backwards curriculum design. How do you start from a set of learning outcomes and figure out how to craft a curriculum around that? And I'll give you a good example of that in just a moment. And then lastly, this constructing the best transfer plan for a transfer student so they're not losing a year of coursework every time they transfer. So this is what I've just talked to you about, the fact that degree requirements, again, Boolean formula over thousands of variables. By picking particular courses, you end up with a curriculum. You can, huge number of curricula for a single set of degree requirements. And then from that, you can create millions and millions of possible degree plans on how you decide to actually structure these courses over, let's say, a 4-year time period. So, there's the number of just degree requirements that you could get from assuming that you've got 40 courses that you're trying to organize. So that's just kind of an upper bound on the search space we're talking about. So let's look at the first kind of optimization problem here. So I'm given a curriculum, and I want to create a personalized plan for a student that maybe satisfies some nice properties. Like I want them to have roughly the same number of credit hours in every term, or maybe I want to have fewer credit hours in the first year, or something like that. Maybe they're an athlete and they want fewer fall credits and more in the spring, something like that. So we want to be able to create plans that can do that. Students come to us with vastly different backgrounds. One of the biggest problems, I think, in engineering programs, if a student comes not calc ready, at many places we say, well, you just can't be an engineer, and that's wrong. We can make that student an engineer. We can teach them the math they need to know. We can do it in a timely manner if we adapt to that student's background. So creating plans that kind of, help a student get back on track, that account for prior coursework that students are increasingly bringing to higher education. Double majors, we have had an advisor who came to me and said, I have a aerospace engineering student who's double majoring in Russian. I don't know what to do. I can't create a plan for that. Help me. right? So this tool can do those types of things. And also then, if you're aware of these toxic combinations that probably shouldn't be taken together in the same term, you can specify them and solve for them. Problem is strongly NP complete, but the instance size tends to be small enough that you can get solutions I'll show you in a matter of seconds, actually, using a high-end solver. So we've got an integer programming solution for this. It's just an assignment matrix that says to put this course in this term with a bunch of constraints that say you got to satisfy the prerequisites. You got to make sure there's not too many credits in a given term, and there's not too many terms or too few terms. We want a 4-year plan. Students expect a 4-year plan, not more. And so this is kind of some of the criterion functions that we've experimented with, right? So you can say, hey, I want a balanced curriculum. Another thing good for learning is let's put prerequisites close to the courses that require them. I wouldn't want to take Calculus 1 in the first term and Calculus 2 in the 4th term, right? Students forget things. And then let's avoid toxic courses. So if you can come up with this toxicity score, then there's a little quadratic function that says I can minimize that toxicity score. So, and we've got a multi-objective optimization using JUMP. Saw today at the talk, they've got some new multi-objective optimization support that I'm very excited about. So here's this is an interesting curriculum. We were doing some work with Colorado State University in mechanical engineering, complexity of 319. Again, this is the summation of those delay and blocking scores across all the courses in this curriculum. And you'll see that for some reason, they've got 20 credit hours in the 4th term and 13 in term 6. And I've been there. I've been in the position of trying to lay out a degree plan, for students, and ending up with this imbalance just because it's really hard. Look at all the prereqs here. Like if I move something, I'm going to make this an invalid degree plan. I'm going to have prereqs out of order. And so you try, and finally you find one that the prereqs are satisfied, and you say, let's just go with that one, right? At least it works. So here I plugged it into our algorithm here that's optimized plan for this curriculum, 8 terms, 12 credit hours minimum, 18 credit hours maximum, and I'm using just 2 of those objectives. Let's balance it, and let's keep requisites close to the courses that require them. It starts running multi-objective optimization. It says best objective 222 based on heuristics, and then quickly 1.37 seconds later, it finds 8 optimal solutions for this. So there's kind of 8 plans that we could give a student. Here's one of them, and you'll see here that the closest the courses are closer together. It's balanced. If you do the analysis on this, 17 max in term 6, 16 in term 1. So you can also solve for those things like I want a little less work in the first term. You can ask the algorithm to do that, and generally pretty quickly finds a solution. Here's a harder problem. Backwards curriculum design. This is how people are supposed to develop curricula nowadays. So you start from a set of learning outcomes. At the end of this program, this student should know these things. And then you say, here's how we're going to assess those things. You build your assessment, and then you pack them into courses. And these are the courses they're going to do that for. So this is kind of the way that curriculum is designed nowadays. Huge number of possibilities, right? Because you're talking about 200 or 300 different learning outcomes that you're packing into 40 courses, right? Think about the number of possibilities there. It's massive. So here's your curriculum graph. You've got an underlying learning outcomes graph. There's dependencies in that learning outcome graph too, and you've got to figure out, how do I map those into this curriculum? How you map those determines the prereqs. If you think about it, the prereqs and the learning outcome graph are actually things that dictate the prerequisites in the curriculum graph. So here's a clustering of learning outcomes into courses, and if anything crosses one of those clusters, that's going to lead to a prerequisite in the curriculum. So here's the specification of this problem. I'm giving you a bunch of learning outcomes. I want you to partition them in such a way that you minimize the complexity of the resulting curriculum. Now, this matters. This matters hugely. There was an experiment at Wright State University. I showed you that EE program where I said the most central course in the curriculum is Circuits 1. What do you need to know to pass Circuits 1? You need to know how to solve one second-order linear differential equation. Yet almost all of those curricula have all of differential equations, that course as a prereq. What happened at Wright State University, they said, well, wait a minute, I'm not going to make you wait 2 years if you're coming a little behind in math. I'll teach you how to solve that differential equation. I'm going to let you take that circuits class on time with your classmates and still graduate you in 4 years. I pulled a learning outcome out of differential equations, and I put it earlier in the program. It turns out when you do that, you actually create a better curriculum because students are actually seeing something, using it, and then still taking the differential equations course. And so it's actually better overall. They actually switched to doing everything that way because the students learn better with that approach. This, we call it the OLA problem. Again, strongly MP complete. Big problem. We've got a pretty good integer programming solution that's based on these two heuristics that I can explain to you later. Here is that typical, we call this a curricular pattern. This is how you get to Circuits 2, right? You got to go through all of these math classes, and I'm assuming a student's coming pre-calculus ready, and it's got this curricular complexity of around 77. This is what they did at Wright State. They brought the curricular complexity down by creating this engineering math first course where they taught you how to solve that differential equation, and you could immediately go into circuits in the third term, just like you could if you came calc ready. When we run our algorithm, we actually can lower that by, and the interesting thing that this does is it tends to take the math topics and break them up into engineering courses. Have to talk to math faculty about how willing they are to do that, but it tends to kind of do more just-in-time learning, kind of an interesting thing that we're finding here. Here's the last problem that we're using. It's called the optimal transfer pathway problem. I give you a requirements tree for an associate's degree, for a bachelor's degree, and a mapping of how courses at the community college map to courses at the university as equivalent. And I want you to create a plan that earns both credentials, the associate's degree, the bachelor's degree, with the minimum number of credit hours. Tough problem. We haven't completely characterized the complexity, but it's got an MP complete problem within it, so it's certainly MP hard. And we have a quadratic integer programming approximation algorithm that's kind of working. We've implemented this in the state of Kentucky for the system of schools in the state of Kentucky. So if you go here and say, hey, I want to create a 2-year to 4-year transfer plan, you pick the KCTCS, which is a community college system, you pick a degree, you pick a destination institution. Here I picked Eastern Kentucky, and a program I want to complete in. At most institutions, you'll get here's how you go from biology to biology, or business to business. With this, you can say, hey, I want to go from biology to physics or business into psychology, and it'll create that plan for you. And so this is the plan that it ends up creating, saying here's what you should do the first 2 years, and here's why. It tells you why if you hit this information button. This counts here at the community college, and here's how it transfers to the 4-year institution, and then here's what you need to finish up at the 4-year institution. And so just now kind of getting that rolled out, trying to kind of make this algorithm, that one takes, minutes to solve or more to get kind of just an approximate solution. So much more difficult problem. But again, both JUMP and use of Gurobi have been hugely beneficial in solving this problem. So with that, if you have any questions or discussion, I'd be happy.
Do I need the mic?
Yell and I'll...
Okay. Thank you very much.
Sure.
Fascinating. How much work does it take to contribute curriculum?
Oh.
I took a look at your website. There's a school I'd love to look at and see how we can compare with other schools, but its data isn't there yet.
Which school? So how much work does it take to enter a curriculum, I think is what you're saying. Yeah, so we have a format. It's a spreadsheet. So if you go fill out that spreadsheet format, it's pretty straightforward to do. I mean, I'll come up and help you do it in about 5 or 10 minutes. We can have one created. If you go onto the website that I showed you, there's also a graphical editor, so you can just drag and drop stuff around and create. That's the other way to do it. So there's either way. What university are you at?
I'm currently at the University of Utah.
Utah, okay. Okay. Oh, yes.
I say this because I'm totally curious, never had any experience with this, but I've heard of people having issues with certain professors, and that's
You've spoken like a student. Okay, so what if you have issues with particular professors, right? Yes, sure. Can you optimize around the instructional thing? So remember how I showed you there's instructional plus structural? It doesn't impact the structural piece of that, but the instructional piece, you could factor it into that. And so, we haven't come up with really good measures for the instructional piece. Like we like the average grade that a student earns could be that in that particular course. But if you could conceivably account for instructors in that, and it's probably an important thing to do. It's what students actually do. Good question, thank you.
So just as someone within a regular course pathway, this would have proved an exceptional if we had in our school system.
Yeah,
So hopefully it can be adopted by more universities as we come along.
Yeah, what Michael's saying, I hear this all the time. Like, why didn't I have this when I was a student someplace? Like, why can't I? People want to self-advise. You want to plug in your stuff and figure out, like, what is the pathway? So, yeah, I hear that a lot.
Thank you very much.
Thank you.